So let's talk about some other issues related to variables. Before we do that, let's define the word atomic. An atomic action is an action that happens all at once. So it can't stop in the middle, it happens all at once. It can either happen completely or not at all. Atomic actions are obviously very good when dealing with threads because it doesn't allow those kind of race conditions to happen, right? If an action has to happen all at once, it doesn't mean that an action can be in the middle while another thread comes in and sort of interferes with that action happening. So we're striving for things that are atomic. And even simple operations might not be atomic, as we saw in our race condition test. So I++ is not atomic. There are multiple steps. It doesn't happen all at once, right? We saw that first you retrieve the value of I, then you do the increment, then you store the value of I back to the variable. So it's not happening all at once, which means something can happen in the middle where another thread accesses the value and then we have problems, right? So atomic means happens all at once. Java does supply us with some classes that represent atomic variables. So these allow us to create variables that support atomic actions. There is the package java.util.concurrent.atomic that has classes that support atomic actions on variables. So we can take a look at that class. And we have atomic long, atomic integer, some other classes here that you can take a look at. We're just going to look at a couple of them now. So we're going to start off by looking at atomic integer. Atomic integer it's to represent integer values, but it's to be used in a multi-threaded concurrency situation. There's some methods get and set, for example, which allow you to just get the value and increment or set the value. There's also increment and get and decrement and get, so that allows you to add to the value or subtract from the value. Okay, so you can take a look at some of these other methods that you can invoke on your atomic integer. Then there's also an update and get method, which takes in an int unary operator. As a reminder, int unary operator is a functional interface with one abstract method apply as int. So that's a method that takes in an int and gives back an int. So this is just some method that you want to apply to your integer. And if you want to do so to an atomic integer, you just invoke the update and get, and then you can send in a lambda that represents your int unary operator method. Okay, so this would be a lambda that looks like, takes in a parameter of type x and returns a value of type x. Okay. Now we can use atomic variables to help us avoid unnecessary synchronization. So synchronization is one way to avoid race conditions, as we've taken a look at. If we have just very simple variables that we're dealing with, though, and we don't want to synchronize whole blocks of code, then we can use atomic variables to help us kind of eliminate that need to synchronize full methods or synchronize larger blocks of code. Sometimes we can get away with just using an atomic variable. So for example, let's take a look at the counter example. And again, to remind yourself, this was our race condition test. So we had the counter class, which just has an integer and then has an increment and decrement. Here right now it's not synchronized, and so when we created threads, each thread invoked 2 increments and 2 decrements on the counter, and we created 500 of these threads and had them all run. So in that case, the value of the counter should be 0, right? It should have no change should be made because all the threads are incrementing twice and decrementing twice. But you can see that sometimes the value is 0 and sometimes the value is not 0. In this case, for example, it's -1. So this was our example of a race condition. Now, one way we could fix that is to make these methods synchronized. So if we added synchronize to the method header, that is certainly going to solve our problem. But another way that we can fix that is by using an atomic integer. So here, for example, is a class that called atomic counter. And instead of using an int, I'm using an atomic integer as the type of my variable. I'm just still calling it C. Okay. Actually, I should probably change that name so it's a little more descriptive now that it's not just an int. Although probably it always should have been a little bit more descriptive. I'll call it counter now. Okay. So here I'm using an atomic integer. I still just initialize to 0. And then inside my increment method, before I just had C++, and now I'm invoking the method increment and get. Inside my decrement method, I'm invoking the method decrement and get. So the increment and get and decrement and get methods, they do return the updated value of the atomic integer. But of course, just like any return value, you have the option of just ignoring it, like I do in this case, or you could also, of course, use it, access it. Okay, and then I can just invoke .get when I want to get the value. So if I want to just know what the value is, I can just invoke .get and use that inside my toString, for example. So let's take a look at the test for this. So here now, instead of that's my atomic counter. So here now, instead of creating a counter object, I'm going to create an atomic counter object and initialize it. In my threaded class here, I'm still going to do the same things. I'm going to, increment and decrement. Let's change this to, sorry, I should have updated these variable names. Okay, so it'll increment and decrement. So again, the ultimate value of this atomic counter should just be 0, right? So every one of our threads in here, I'll create 5,000 of them, are going to increment and decrement that value twice. So ultimately, the counter should be 0. And when we run this program, we can see that it is 0, and you can see that there's multiple threads running here. Again, that number isn't 500 because some of the threads will have already stopped by the time we get to that thread count line. They'll have already done their job. But no matter how many times you run this, it will always be 0 because the incrementing and the decrementing are happening all at once. So that's a way to avoid that race condition. So again, if all you're kind of needing to do is update a single shared variable and you don't want to synchronize, you'll notice here that these methods are not synchronized, right? And they don't need to be because the code inside is just is atomic. This increment and get method is atomic. So invoking this one line of code is atomic, so we don't need to synchronize that method. So using these kind of atomic variables can alleviate the need to synchronize blocks of code. There is also a class called long adder, and there's also long accumulator, double adder. Okay, so these are going to kind of parallel to, and double accumulator, these are kind of parallel to the long adder. What this allows you to do is basically just, it's designed to represent the functionality representing a collective sum. So if exactly kind of what we're doing with this simple counter example, if you have tons of different threads working on code, but they're all kind of contributing to the same sum, you can use a long adder. Okay, so what that allows you to do is it allows you to have kind of, this thread has the number 10 and it's adding it to the sum, and this thread has a number 2 and it's adding it to the sum, and they're all kind of adding to this collective sum. They're accumulating this value, but that accumulation is coming from multiple threads. Long adder is exactly the class to be able to do that, to use to do that. Okay, and there are some methods in long adder. There's add, where you can add a particular long value, or there's increment, where you can just update by 1, and then there's also a sum method. So let's take a look at long adder here. Okay, so that sum gives you the current sum. So the way this works is that it's sort of the long adder object will kind of be taking these values in from multiple threads, and then you can invoke sum when you want to get that result. Okay. So, for example, we could actually use this instead of creating this atomic counter class. We can just use a long adder. So I don't even need a separate class. I can just say, hey, let me just have a long adder. And then in my thread class, I can create an object of type long adder. And let's rename it so it's a little more descriptive. Right? And then inside my run method, I'll just increment it, decrement it, increment it, decrement it. And again, I'll do a bunch of threads, and these should all be 0. So again, if this is the idea, if you are having multiple threads contribute to a sum, you can use a long adder object to do that. And again, you don't need to then worry about synchronizing that code because the changes of the value to the long adder will be atomic. They'll happen all at once. So there's no chance of being in the middle of an increment and having another thread come in and get that value like we saw when we just use a regular int without synchronization. Okay, so these kinds of atomic variables can be very useful for when you're doing simple things like keeping track of a running sum or calculating a single value. And even atomic integer doesn't have to be simple things, right? You can use this update and get method to put in a very complex method that you want to apply to a variable. But these are essentially for use when you're keeping track of a single variable, and that single variable is going to be accessed by multiple threads. Okay, so that's what these atomic variables are good for. And again, there's a couple of them in this package, and you can take a look at some of the others. They're kind of parallel to the ones that we just looked at. Now, one more note I want to talk about in this section and in this particular video is the keyword volatile. So volatile it's a little tricky, and you have to really use it with caution, but I do want to cover it because it might be a term that you'll see, and it certainly could be a term that you could be asked about on an interview, for example. So I do want to talk about what it means, but you really have to show extreme caution in using volatile in your code. So essentially, this is what volatile is all about. If a thread changes the value of an instance data variable, you would expect other threads to see that change, right? So if a thread updates some value, you'd expect to be able to go in with another thread and view that value. But that's not always the case. And the reason for that is that the Java virtual machine does allow values to be temporarily stored in working memory, kind of think about that like a cache, rather than in the main shared memory, which is the heap. So one thread could access that value and change it, but it could still be temporarily stored in cache, and then some other thread could come along, get the old value from the heap, and they don't have that new updated value. Okay, so this is another place where you can have a problem. So one thread, again, changes an instance data variable, but it hasn't been taken out of cache and put back into the heap. And another thread comes along and gets it. And so it's getting the old value. So this is another example of a problem with shared resources. Now, if you declare this variable as volatile, that's a keyword, that will guarantee you that the value is going to be read from main memory, which is your heap, rather than from local cache. So it essentially assures that the reading and writing of the volatile variables is atomic, that those actions are going to happen all at once. Okay. Now, reads and writes of variables other than longs and doubles are already atomic. So when you read and write an int, for read or write an int, for example, from main memory, that is an atomic action. But if you read or write a long or a double, that's not. If, however, you make that variable volatile, then it will be. Now, it's really important to note, and why I say that you need to be really careful about this, is that volatile does not mean synchronized overall, okay? Or, sorry, I should say atomic overall. Sorry about that. That was actually an old version of the slide that I'd updated. I wanted to make sure the update was correct here. So anyways, okay, so declaring that variable is volatile enforces that all the updates will be written back to heap memory right away, and it assures that that reading and writing will be atomic, so happen all at once, okay? So again, reads and writes are atomic for most primitives and for reference variables, but they're not for long or double. If you make a long or double atomic, then, I'm sorry, volatile, then that reading and writing will be atomic. Okay, so making it volatile does these two things. It ensures that the reads and write are atomic, and it makes sure that the declaring, that all the updates will be written back to heap memory right away. So you're not going to have this potential problem of an updated value being stored in cache and not being put back in the heap. So when a new thread goes in, it knows it's getting the value that's been updated and written back to the heap. However, volatile is not the same as synchronized, so it does not mean that all of your actions are atomic. So if you have a variable that's declared as volatile, and you do, for example, my volatile plus plus, this is still not atomic. This still, you have to get the value of the variable, you still have to update it, and you still have to write it back to memory. Those actions of getting and writing are atomic, but that three-step process is not. Okay, so volatile and synchronized are not the same thing. So volatile, it might be good enough if you have the situation where you have one thread that's updating a value, a variable, and lots of other threads that are just reading that variable. Volatile might be good enough in that situation, and I say might be because it still depends on other things. But for sure, if you have multiple threads that are updating a value, volatile is not good enough. You have to synchronize that code or use an atomic variable. Okay, so volatile is kind of, it's good enough for very specific situations, but you have to use it with extreme caution because there is a very narrow set of circumstances that can apply. That being said, it is a good keyword to know. It sort of pops up on interview questions. I don't know why. It's one of those things that, like, I think it's supposed to be like a gotcha question. So it's good to have some familiarity with it. You also might see it in code, in other people's code, but just be really careful about using it in your own code because all it does is it guarantees these two things, but it does not guarantee synchronization. Okay, and it does not guarantee atomic actions or atomic actions that use that variable. It just guarantees that the read and the write will be atomic, and that the writing will happen to heap memory right away. That's the only thing that volatile does. Okay, so there's a little overview of atomic variables and volatile, and that's just kind of a couple more things to add in to your toolbox related to concurrency.